Hello everyone. Today's lecture is the module over principal idea domain. I divide this chapter into two parts. So in this part, I want to talk about this focus. Let's talk about FGAG, in short for finite generated Abelian group. Every finite generated Abelian group, the point is here. Every finitely generated Abelian group is decomposed these forms. This means the GM1, this is the integer GM1 direct sum of GMT, and remaining part is the direct sum of the integer. In particular, these forms people call this form is Torsion subgroup, and the remaining part is the Torsion free group. Torsion free. Okay, and let's see one of the example. If consider G n is the integer, and suppose n is the prime factorized PR1 blah 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 p k r k, where is the pi or index in I in prime, and ni is the positive integer. Okay, then Gn is one of the decomposed way is Gn. Clearly Gn is the finite generated Abelian group. Okay, and then because this is finite generated Abelian group, this is decomposed Gp1 and 1 direct sum, Gp2 and 2 direct sum of the Gpk Rk. This is decomposed into this form. Of course, in this case, there is no Torsion free group. Another remark is the definition of the Torsion subgroup and Torsion free. Torsion subgroup, the definition of the Torsion subgroup GT means the collection of the group element such that mg is equal to 0 for some positive integer in G. Of course, G is the clearly Abelian group. Just for any Abelian group, if this collection of G such that mg is equal to 0, then this is a Torsion submodule. Literally, when m times sums, this come to the identity in element. This is Torsion subgroup. And however, if the element is the only 0, group element is the only 0, then GT is called Torsion free. This means for any times m multiply except from 0 element in 0, it does not come back to 0. For example, in this case of Torsion subgroup, it's just in this case G2 plus G3 is clearly, for example of the Torsion subgroup is G2, direct sum G3 is the Torsion subgroup, because this is element is the AB, where is the A and an element in G2 and B in G3, and we can say for any element in A, B, choose, for example, 1.2, okay, then when some time multiplies term, it comes back to 0, comma 0 of identity, okay. And however, rational number Q is case of the Torsion pregroup, because we can choose for any rational number B of A and investigate MA over B is 0. Of course, AB is element in Q. Then the element is MA over B2 is equal to 0. For any rational number is given, never can make 0, just m times counts. Only 0 can be the element is the satisfies this equation. So this rational number is the quotient. Rational number is the Torsion free group. Then this slide is so reasonable question. Every finite in case of the group, every finite generated group is decomposed here. And in case of the R module, is there related theorem which is similar to this? Today's lecture is the main topic is to check this theorem. Every R module, when every R module is decomposed, the Torsion free part and Torsion submodule part. But to decompose these guys, we know some conditions are necessary. This is our main topic, one of the topic, the PID, in short for principal ideal domain. Let's recall the concept of the ideal, which is around in the abstract algebra. Historically, ideal is made from the generalization of the multiplication. But in fact, the original definition, this is so very useful when deal with everything. Let R be a ring and S be a subring of R. When it comes to S, is the subring of R. This is clear. See this definition here. 0 is clearly in S, and for A minus B in S, for all A in BR. And S RA, okay, RA is also contained S, where is the A is the element in the R, and A in S and R in R. When this satisfies, then S is subring of R. Then such subring, in this case, such subring R is R ring of R called ideal. When in this case I satisfies this condition, and if delete here, in this condition, under the subring condition, AI in I for all in AR. This is so-called left ideal. And IA is also in A for all elements in R. This condition is the right idea. So for all ring element in R, left ideal and right ideal satisfied, then I is called ideal. So let's study recurrent principal ideal domain. This is the composition word, principal ideal, ring plus integral domain. So rather using the concept of the principal ideal ring, because of the profuse properties of the principal ideal ring with integral domain, we frequently deal with PID rather than principal ideal ring. Okay, so let's see the definition first. An ideal generated by a single element is the principal ideal. This means when ring R, this is the ring, and we clearly want to observe an ideal, but all of the ideal is written as the single element generated by single element A. This means this is the notational. A means, this bracket means element in RA means R in R. So literally, the ideal is generated. The multiple of R. So when we directly show that this set, just bracket is using the definition, and this set is clearly satisfy the definition of the ideal. This means AR, clearly this is the subring, and RA is in A. Let's see just the definition of the set theoretism, the theoretical relation. This is clearly ideal, and this is generated single element, then this is the principal ideal. But important thing, for any idealist thinking, this should be always this is always written as the single generated form. Okay, so for example, when you consider integer is a ring, clearly ring, then every ideal is the written as some integer element. So integer is clearly principal ideal domain. So as I said, the principal ideal ring with the integral domain is called principal ideal domain. So integer is clearly integral domain. So this is so-called important representative example of the principal ideal domain. And as I said earlier, principal ideal ring which is the integral domain is called principal ideal domain and PID. Because of these profuse properties, we and some people use the PID rather than just principal ideal ring. One of the properties of PID, I remember, is that every principal ideal domain is clearly unique factorization domain. So the unique factorization domain means the domain, integral domain, which is the prime when the factorization method is the unique up to the order. So this, for example, we know integer g is clearly principal ideal domain, but by this theorem, integer is unique factorization domain. That means that every integer in G is given, then G is the unique factorization P1, R1, PK, RK, some prime and some prime members. Then this method is unique up to except from the change of the order, changes of these numbers. So this is so-called the fundamental theorem of arithmetic. Okay. So, apart from these properties, there's lots of properties of principal ideal domains, such as the Noetherian ring, and so on. So this principal ideal domain is important to understand the abstract algebra. And let's change the topic. Our theme is the PID into the Torsion module. We know every finitely generated Abelian group is decomposed to Torsion subpart and Torsion prepart. Okay? And first, if we believe every R module is decomposed to something like this, this is clearly exists Torsion part and Torsion prepart. Okay, this is the theorem which is related to define the Torsion submodule and Torsion pre in the sense of the R module. So let's read the theorem. Let A be a left module of the integral domain R. We can understand this is just a principal ideal domain, but in this case, the principal properties does not use. Just in this case, these theorems are satisfied integral domain, and for each A in A defined, OA is defined here. This is the element in R. This is OA. Yeah? And this is this collection of the R such that RA to be 0. And the theorem here, OA is clearly ideal. This is called, it has the name order ideal, but the name is not useful to discuss with the total concept. Prior to prove this statement, if we believe this theorem is true, in other words, in case of statement B, if AT is the submodule of A, we can say AT is called a Torsion submodule of A. The definition is reasonable when compared to the Torsion subgroup in a group. When we consider the definition of the Torsion submodule, Torsion subgroup is the element in G such that mg is equal to 0 for some m is positive integer. If the element in G, the collection of G is the Torsion subgroup if G is only the collection of the element is unique element is 0. For example, except from 0, if apart from 0, this equation does not satisfy, then we can say this is the Torsion free. The group G, okay. In this case, the group G is Torsion free. In this case, we can say if AT, in this case, AT means A collection of A in A's, OA is non-equal. If we understand these words, for some element in R, the collection of in R, such that RA is equal to 0. So if this element is also equal to 0, then we can say the group A is Torsion free. The R module, in this case, the R module is Torsion free. And if this collection of set is non-equal to 0, then we can say this is just this. In this case, is called Torsion subgroup, and this is Torsion submodule. Now let's prove the statement A. Claim is OA the ideal R for HLI. To check the OA is the ideal, we can first thing we can do. OA is an ideal. OA is a subring of R. The definition of subring is clearly OA is the collection of these guys, because 0 is clearly R, then 0 is OA, okay, and OA, we can do more precisely, 0 is equal to 0A. So 0 is clearly element in OA. Second property is if we x, y contained in element in OA, then this means there exists R as in element in R such that x RA is equal to 0, and in case of y is also equal to SA is 0, and x minus y means R minus SA, and because R and S are linked, clearly the subtract is clearly element in R, and this is clearly 0. So x minus y is also element in OA. Finally, if R prime in R and x element in OA, this means again for there exists R such that RA is equal to 0. Then R prime x means R prime RA is equal to 0 to begin with, because RA is equal to 0. And if I want and we can say, because R prime and R is element in R, so we can say that by the associative rule R prime R A. So because this is element in R, this equation, so R prime X is equal to OA. Because OA is a subring of R, so then we will prove MOA is a subset of the OA, and OAM is subset of the OA for all element in MR. Let's check this, copy this, then prove this statement. The first thing is suppose MOA written as the MR is element in MOA. If we finish the proof, the form is clearly, because MR is an element in OA. This means MRA is equal to 0. If the statement is true, then we can deduct this from here. This is here because in this case element in R, in this case R is element in OA. So you can say 0 is the RA. Okay, this means 0 is equal to 0 M, and this is we can say RA in 0 is, it is better, M equal to M times of 0, and this is MRA, and M is element in R, and R is element in R, and A is in A. This means by definition of the R module, we can say the associative rule, we can say MRA. The properties of the definition of the R module. So our desire is MRA is equal to 0. This is equal to 0. So this, from this here, MR is element in subset of OA. And this is analogous step as in this case. So if RM is element in OAM, this means R is element in OA. In this case, let's directly calculate this element to this guy's content to OA, means RM A is equal to be 0. Then in this case, because R, as I say, R and M is element in the, in this case, let's see, R and M are element in ring, but this guy is the integral domain. What is integral domain? It's important. When you consider this, integral domain is ring to begin with. This contains means ring with unity, and commutative is warrant. So this means we can say, because this commutative, so we can say this is RM mr is equal to a. So if we change this equality is because R is integral domain and integral domain is commutative ring. Okay, then in this case M and R is an element in R. Okay, this is ring element and this is the element in additive group, and in this here definition of the R module we can say M R A, and this is 0 in this case because R is contained OA, more precisely because R is contained OA, this is clearly 0 and this is 0. So we can calculate RMA is equal to 0. So RM is element in OA. So because we prove this statement, we can check OA is ideal of R, so-called order ideal. And statement B is the AT is submodule of A. The first thing we can check is the AT. The definition of the to become AT is to become of a submodule. AT is the submodule of subgroup of A. In other words, AT is subgroup AT is subgroup of A. Check this. First, the operation in additive relation is clearly preserved in this set. And identity, if we additive group, identity 0 is clearly A. Then our claim is this is identity. Identity A zero in A is also in AT. Okay. This means if I want to claim 0 also in element in AT. This means if we clearly 0 is an element in A, then we'll claim OA means the collection of the R such that RA is equal to 0. In this case, because A is 0, in this case, 0. So, if we consider if we find element R times 0 is equal to 0, R is not to be this equal to 0. So, any element in R can be a 0. For any element comes, R times 0 is equal to 0. Only element R is not unique in 0. This means O0 is not the 0 set. So 0 is, in this case, from this here, 0 is element in AT. Another claim is here. If A is element in AT, there exists unique element in bus such that in this case, because this is the additive subgroup, A plus A inverse is equal to 0. In this case, additive Abelian group is minus A. In this case, we claim is A inverse should live in AT. This means we can say this is pick minus A because A is equal to element in AT means there exists some element in R in R. This is non-zero element such that RA is equal to 0. Okay. This implies here. So from this here we can deduct from this statement we can deduct R minus A is non-zero element. Okay, R is non-zero element. This is also equal to 0. So we can find minus A is element in AT. There exists non-zero element such that R minus A is equal to 0. So clearly minus A live in AT and A plus minus A is equal to 0. So we can say in this form here, AT is a subgroup of A. So if we prove AT subgroup of A, the remaining thing is for all element in R and for element in XAT such that in this case the notation problem M is element in R and R is element in A is element in AT such that MA is also AT for all elements. The method to prove this is directly calculate this here. MA is element in AT. This means there exists some element in R such that this non-zero element R MA is equal to 0. From this here, by the assumption there exists element in R such that MA RA in this case RA is equal to 0. From this here we can get this statement. So this means 0 is equal to M RA because Ra is equal to 0 and M is element in R and R is element in R. By definition of the R module, we can say M R A. And as I said, this is the integral domain. Integral domain is commutative ring. We can say R M A. And again, we can say R M A. So our proof is finished because R M A is equal to 0. So this case, AT is the submodule of A. The last property is just introduced, not the detailed proof. This is related to the first isomorphic relation theorem. The important role of the idea is the construct of factoring, and the factoring is isomorphic to something. In this case, R and equal to, if we consider RA. This is just a collection of just RA in R. If we easily check, this is the homomorphism relation, ring ideal. And if we factorize because clearly this is the ideal, so-called order ideal, we can factorize this is R quotient OA. This is the set element R plus OA. This is R is equal to R. And we can give the natural homomorphism psi. In the previous lecture, we can refer this set again. This relation, unique homomorphism via RO quotient of A to RA given by I plus OA goes to phi R plus OA defined as phi R. This is psi. This is unique homomorphism, and indeed you can show indeed corner phi is equal to OA. This means from this is if and only if relation R quotient of O alpha OA is isomorphic to RA. This is we can get this isomorphic relation, this first isomorphism theorem, isomorphic theorem. And let's talk about the relation between the pre-module and Torsion pre. The relation is here. If let R be the integral domain with identity, that is integral domain, then every pre-module, if F pre-module implies Torsion pre. But the third point is the converse statement does not satisfy. So every pre-module can be a Torsion pre, but does not satisfy the converse statement. To check this, suppose F with a pre-module and choose the element V in F. Then then when considering the definition of the premodule, V is written as Ri Xi. Where is the Ri is the element in R, but this is specially in integral domain. And Xi is consists of bases. For convenience, X is the we put the X is the element in basis such that this commutative relation is satisfied. And our claim is here, for convenience, put the Ft is the consists of the, in this case, the subset of the submodule. We prove this is this type of the element is the submodule of F. Okay, and when we consider the definition OV, in this case come to OV. This because in this case, because it's the non-zero element, there exists non-zero set. There exists non-zero element. Such that RV is equal to 0. Our claim, because Ft is the frame is because the premodule is Torsion free, the collection of the V is indeed only the zeroth vector. To check this, let's consider, suppose when you choose the element in V, RV is 0. Where is, in this case, R is the non-zero element in integral domain. Then, because we can say V is the, we can express V is the here. So R, we can say Rx xi, and this is the by the property of the sigma Ri Ri xi, and this is 0. Because the xi, the basis of the x, this is clearly linearly independent set. So R, all of the element in I, R product Ri should be equal to 0. But this is the element R or Ri, or an element in integral domain. The reason is important, the condition of integral domain. So, and we can say we choose the R is the non-zero element because this inequalities O V is not equal to 0 set. Then we can say this is integral domain. So if this is the non-zero, the way this equation to the only method of the equation satisfy Ri just be 0 for all I. This means the element, the coefficient of the Ri is always 0. So this means ft is the 0. ft is the 0 set. Our claim is satisfied. Let's see the counterexample of the converse statement of this here. This means every Torsion pre does not imply Torsion. Every Torsion pre group is not pre-module. The example is concisely rational number module of the integral domain. In the first slide, we show rational number Q is the Torsion pre. Okay, this is Torsion pre, but this is clearly non-pre. This non-pre. This is the reason I remarked or proved in the lecture 5 maybe, but again prove this statement by the contrary. Suppose Q is the pre-module, then there exists some element 1 or A in rational number Q, because this is composed, not only this is the direct sum is the one component. This is the one element basis, such that A, the basis A, is generated rational number. In this case, the basis, okay, single basis generated rational number, because of this not composed of direct sum, only single number, and this means Q is the cyclic group, because single element is the generated whole set, and cyclic group is decomposed GM if the element is the finite, but this is clearly not finite. This is clearly isomorphic to integer, because this order is the infinite. But this is contradiction. Rational number is isomorphic to integer. So this is not a non-pre-module. Let's see again the relation between the pre-module and Torsion pre. If the R is integral domain in unity, every pre-module is clearly Torsion pre, but not vice versa, because of the rational number Q as the counterexample of this relation. But our natural question is that when the converse statement satisfies, the answer is the change of the ring condition and the change of the module condition. So two conditions are changed, we can turn into the converse statement into true statement. The following theorem represents the answer. Let's see this theorem. Let's read this theorem. To begin with, check. Torsion pre-module A can be a free, the converse statement satisfied. Then when this satisfies, a finitely generated Torsion pre-module of A over a principal ideal domain. This is because our protagonist come to write the principal ideal domain. Okay, so the condition is here. every finitely generated. In this case, the reason why this condition is necessary, as in case of the rational number q is non-free, that means this does not generate a finite element. So the finitely generated condition is necessary. And overall principal ideal domain, this condition is claimed. Well, it's also important. This is when these two condition is the given, then every Torsion free module A is free. I'll not prove this statement. When the reason of principal ideal domain, when you see find the proof of this statement, you can find why the principal ideal domain is necessary. Okay, so important theoremism is in order to satisfy the converse statement, these two conditions is necessary. Then we can get the following theoremism. If A is the finitely generated module over principal ideal domain R, then A and in this module which is satisfied this condition is decomposed and Torsion submodule and Torsion free, whereas F is isomorphic to A quotient of AT. Then this is the answer, also answered our first question in the introduction of the lecture. I said every finite generated Abelian group, the condition is important. Every finite generated Abelian group is always decomposed to Torsion subgroup part and the Torsion free module part. Torsion free part. Then I questioned the first slide, when this module is decomposed, looks like Torsion subgroup and Torsion free. The answer is finitely generated module over a principal ideal domain. Again, this is important. It's written right again. Finitely generated module, short abbreviated FGM, and R is clearly principal ideal domain. So every finite generated module of the principal ideal domain R, if A is the finitely generated module of principal ideal domain R, when this condition is given, then looks like the group decomposition theoremism, the module of R is concisely decomposed, concretely decomposed the Torsion submodule part and Torsion free part, and the Torsion free part is isomorphic to a quotient of AT. This is Torsion submodule, and looks like the group we can get F is also isomorphic of G quotient of GT. So this relation is also analogous to this theoremism. This is the very reasonable rational result when considering a quotient of AT is isomorphic to M. M is the Torsion free part. Okay, so let's prove this claim. For convenience, I put the set M is the collection of the quotient member of the quotient group. Because this is the Abelian group, the form is written is here, A quotient T such that O A plus AT is non-zero set. If this set is the Torsion A or quotient of AT is the Torsion free, our desired result is this only consists of the 0. But in this case, this is the quotient group. The form is the AT. Okay. So, if when this concerning definition, when choose the non-zero element in R, such that we can say R A plus AT is equal to, in this case, quotient group AT. And we can expand by the operation of the quotient group. It is written as RA plus AT. So when considering this equation are satisfied, this star, in order to star is satisfied, the answer is the RA is also element in AT, means the Torsion submodule. Because this is, if this is contained this is contained AT, this is just element in AT, so this is equal to AT. Okay. Then this is not just a common set, not a common set. This is the Torsion submodule special set. This means there exists R per convenience R prime. This is also non-zero element in R, such that in this case R prime R A is equal to 0. Okay, this is definition of the AT. And if we believe and R prime and R is the element, non-zero element in ring, anyway ring, and so we can say by the associative rule, we can say R prime R A is also equal to 0. And again, R prime is the non-zero element, and R is also non-zero element. So when considering this here, A is also A is an element of the AT. Then our proof is finished, because A element in A is also in AT. We can say A plus AT just written as AT. So the correction of the M is in fact indeed AT. Another important point is that A quotient AT is Torsion module. Okay, the reason is here. And because A or quotient A of A is the free, Torsion free, A is the finished proof, the statement in claim. And if this is Torsion free, then this is Torsion, this is free module. Why? In the previous theorem, finitely generated module over a principal ideal domain R is free. Okay, because this is finite generated condition, but not only finite generated condition, but also principal domain condition. Because this converse statement is satisfied. And the last on previous slide, we proved A quotient of AT is the pre-module, but this because FA is the finitely generated, so we can say this is the pre-module with finite basis. And the interesting point in this proof is to begin with, F is the pre-module, and let's construct the interesting point this proof following exact sequence. This means 0, AT, and A. This is contained clearly, submodule, and quotient set, and 0. This form is clearly exact sequence form, okay? But if we're using the theorem we learned the lecture 5, first, A quotient AT is the pre, okay? But pre-module over a ring R is the projective. And projective ring is given, the following statement is taking following equivalence relation. Following exact sequence is short exact sequence. Then this means we can say A is isomorphic to AT plus A quotient group of AT. Then this is the final of our claim. This is the Torsion submodule part, and this is Torsion pre-part. So just change this. This is just F. This changes the text F. Then we can get the result if we just change the F. So every finite generated submodule, every finite generated module over a principal ideal domain is precisely decomposed Torsion submodule part and Torsion free part. This free part in precisely is the A quotient of AT.